Mitch and Robert, I'm really glad to greet you in our podcast. I will give the floor to you.
Yeah, well, thanks for having me here. My name is Mitch Pryor. I'm a senior research scientist at the University of Texas at Austin. Founded the Nuclear and Applied Robotics Group in, 2008 now. So it's going on to its 15th year. Sort of the background there was really understanding that to put robots into these hazardous environments, nuclear, oil and gas, defense, et cetera, we really needed to take more ownership in the universities of building the technology to a level where it could actually traverse what they call the Valley of Death. That idea that we come up with really cool ideas in the university, and then how do they possibly become commercial reality? And I think too often the universities dismiss their responsibility in getting that done. So we've done a lot of work there, and when we try to focus on making sure the robots can get across that, sort of the research topics that come up are not only surviving the hazardous environments, which usually means that the students have to learn a little bit about the domain the robots are going to go into. So students take nuclear courses. Students take oil and gas drilling courses. They read handbooks and learn some of the stuff that might be coming out of the imperial war colleges that allow for tactics. But then as far as research goes, the areas where we really find ourselves therefore having to work are long-term autonomy. I mean, it is great that we can get a demo to work for a minute and a half or 2 minutes and get a video of it, but what we really need is a robot to work 24/7. So can we do a demo where the demo is 40 minutes long and we do it 10 consecutive days in a row without too many mess ups or errors or minimal number of errors. So long-term autonomy, and then the situational awareness or human-robot interactions. If the robots are going to be deployed in the real world successfully, it is not going to be PhDs that are interacting with the robots and debugging them in real time. We can't call Robert to fix all of our problems, though we would certainly like to. What we really need is that soldier, that technician, to be able to work with the robot and to want to work with the robot, because our goal here is not to replace the operators in these environments. It is to remove these operators from the areas of harm and to allow them to focus on the more interesting parts of their jobs where we still absolutely need humans in the loop, and not the parts of the jobs that are dull or drudgerous or dangerous, the 3Ds as we call it. I'm leaving a fourth D out, but it's good enough for now.
You left my mind blown with the introduction. Quite lovely.
Okay.
So many questions, so little time.
No problem. But with that, I'd pass it over to Robert, because I think that he is certainly one of the people here at the University of Tartu who recognizes this need of transition, and particularly with where he's both working and completing his thesis. Definitely both hit that mark.
Yeah, I guess that's the part where I introduce myself. Right, yeah, I am a PhD student over here, University of Tartu, in Intelligent Materials and Systems Lab. And now that we have recognized that there's the need for this long-term autonomy system, and there's a huge variety of tasks a robot could do. So Mitch did mention a couple of them. And there's a huge variety of robotic hardware, robotic software, and now they all have to work together in this synergy, if we will. It shouldn't break down. It should work 24/7, like Mitch said. And for that, for one specific task with one specific robot, you could put together a software, and it works just for that. Then for a different task, for a different configuration of robots, you go back to the drawing board. You create a new software framework or task, or implement a different kind of software. But this doesn't scale, and this gives a lot of reliability-related problems. So my work focuses on how we can abstract or create a framework for autonomous systems, that if I have these tasks, 5 different robots, or let's say, 3 different tasks, 5 different robots, different ways of controlling them. One of them is completely autonomous. The other one is a half autonomous, operated by a human or supervised by a human. How you put the system together, and my PhD work focuses on this autonomy framework for such particular cases in the light of long-term autonomy.
If I were a student, I mean, I listened to you guys, I would be overwhelmed by the sheer amount of possibilities, where to put my brain activity in these fields, what to do, what to research. So what would be your cue points for the starting students, for bachelors and masters and even doctoral students alike? What would be the place to be?
How do you get to this point, kind of?
Yeah.
Sure.
I could start with one of the things that I really like about the University of Tartu and how things are organized is that you could almost say that at the bachelor's level with students taking my course, they're really mastering the tools, the robot operating system, ROS. You guys got these excellent labs, and people are learning the hardware and the software fundamentals of how things work at the bachelor's level. At the master's level, I feel like it is exactly there in the word masters. I'm going to take one particular area, navigation, component integration, manipulation, grasping, whatever it is, and I'm going to master that topic. My job is to become really good at that particular aspect of robotics. Someone who becomes a master of a topic then recognizes the deficiency that might still exist in that area. That's what then becomes proposed as a dissertation and then hopefully a PhD that then fixes it. The great thing about this setup is that people can graduate with a bachelor's, and if they don't want to continue on to agree, they have the tools to go out and get a job. If they decide that they want to be able to solve harder problems, they then pick an area and they master it. And then if they recognize, wow, we still stink at this thing, or there are still things that can be done, then they recognize and propose where their area of contribution is to fix that problem. And I think that that's definitely where Robert came into play here. The first individual that came as a postdoc to the University of Texas was Carl Krusame, who's a professor here. We were actually introduced by Alan Tachik, forgive me if I mispronounce his name, and my nuclear colleague Sheldon Landsberger, who worked on the nuclear side, met at a nuclear conference and recognized that there was talent at both schools that should be introduced. Alvo Ablu, and again, gosh, you're going to laugh every time I say anything.
The letters were correct.
Yes. Came across. Estonian's hard. I just, came and we met and we were able to kind of get this interaction going. What happened then was Carl came in and mastered kind of ROS and brought that back here and worked on some demos that we wanted to do where we had robots being directed by hands-free. You would move your hand in space and the robot would move. And we learned how to scale our hand motions so that we could use a hand motion to direct a robot to move across a lab. Or we could scale the motion small so that the motion of our hand scaled down to sub-millimeter action so we could thread a needle with a robot. And I, as the high-level hoiky professor, kept saying, that's really cool. Can you do this? That's really cool. Can you do that? And they kept adding stuff until our code base was this giant spaghetti piece of horribleness that when I came up, that's great, add something new. The students had to go and for a weekend and cry in despair and figure it out. And then finally Carl and Veiko Vundar came to the lab and were like, all right, how are we really going to set this up? How should this really be set up so that we can react to all of these new tasks that this crazy man is giving us? And that, I think, is what became, the PhD topic, where they had mastered the capabilities, recognized the real problem, and then as their PhD solved it. And so to answer your question, that's the pattern that I think allows a robotics program to succeed for the companies, for the students who want to solve tough problems, and for the advancement of robotics in general.
I have nothing else to add. I mean, it will be a waste of time. So I agree.
So awesome. That's so awesome. I remembered a saying from our professor Alvo Ablo, who said that a
Thank you for saying that correctly on the record.
The letters were correct.
He described a problem in robotics, which is making the robot arm that we have here aware of itself, that it's in a three-dimensional space actually, so it can't move through itself. That would be a rookie mistake to program it into a like movement or of a robot. So how much of a rookie problem is that compared to the autonomy part of the automatization part of the robotics?
It depends. Of course, in a surface level, it's a rookie problem. You don't collide with yourself. But then if you need to increase the controller frequency, like, for that, in order not to hit yourself, you need to do collision checking and things like that. There are cool algorithms that do it analytically, meaning that you plug in a number and it tells no collisions, or vice versa. Or you just go and check it every loop in your system. So I wouldn't say it's a rookie mistake. It depends. But what was the question that followed up that?
There's a great analogy here that you learn, like if I was to ask a bachelor student to write a collision detector for this, they would hate life for that. I hate life. They would learn a lot in that that project. It would be very difficult for them. And so, you learn how to you learn how the cameras work. You were explaining to me how the microphones and the different charges and things like that. But then in the end, there's a tool and a button, and now you understand what's happening behind that. The same thing's true with collision detection. Like when you're first learning it, the first time I had to write a collision detector for a robot, either in class or to make sure a robot didn't hit itself, it was hard. But then we got it running, and we hopefully designed it in a nice software package, and now everybody else can use it. So to somebody else, it may seem easy because we've black boxed the problem. And that, I think, is the goal of a lot of what happens in robotics. So I don't know if it's correct. It's a hard problem to solve, but luckily people have solved it, and we can use it, and now I take it for granted that it's easy.
Yeah, and you got down to the application part of things that you as engineers and you people have to know the bits and atoms behind the buttons, right? So when it comes down to application of robotics and the future of robotics, I mean, the middleman, the person who's consuming all these buttons and stuff, how crazy would this functionality of a single button press get in your wildest imaginations and fantasies in the near future? For you guys as engineers doing the bits and atoms, how crazy can this thing get? Like you push a button and basically you get a hologram from Tupac who resurrected and performs you a song about, I don't know, doing some robotic stuff.
I'm going to recommend that Robert talk about the ChatGPT demonstration that you, Fabian, and Selma put together, because I think that really gets to like, there's a button.
So I first ask, can you repeat the question? What was?
I think the brass tacks would be, what will be the future for the end consumer be like for some robotical applications?
So, well, I mean, the end consumer, I get what you meant by that, yeah. But in order to answer that, the end consumer, much like us, who don't think about actually collision checking, that we take a soft piece of software that somebody created, we know it works, and apply it to our bigger system. Similar to a consumer, even these days, they don't need to actually really need to think about it. It's the developer or the engineer in the middle who needs to go through the whole headache.
Yeah. So let's take it from here. What kind of engineers do we need in the future? I mean, you let them, your students study nuclear stuff, and I don't know, definitely they will need to have some skills in welding and different skills to know together stuff. And
I guess naively
Would you need to be a practical person, like a pragmatical person, like a tech savvy? I don't know.
If I should throw a number, so I would say in 10 years, you don't need to be worried about engineering work like, plumbing, welding, being a carpenter. That's solid, because, it's really, really, really hard to do textures, things that, carpenters or welders are doing. But there's a tendency with that we kind of automate a lot of things with the even ever-growing progress. So I guess within 20 or even 30 years, that's going to be a big question. Like, who is the engineer? What's the role of a roboticist? Is it figuring what level they're figuring out? Because we cannot, at the end of the day, the focus of an engineer is definitely shifting. And yeah, it's just so hard to predict that. Maybe you have something to add on top of that.
I think that to get to it a little bit, in computer science, they have the idea of this full stack developer, the person who can do everything from the low level, get things off the drive, all the way up to like the web interface on the front end. Robotics are infinitely more complex, and you have to add mechanical aspects, the welding, all that kind of stuff to develop them as well. So it's going to be increasingly hard for anybody to be an expert in all the things that are necessary to be a full stack roboticist. People need to understand what all of that means. And then you add to that the fact that these robots eventually need to be deployed in different environments. And if someone says this environment is 50 millirem versus 200 rem, is like, someone even know what that means? Those are units of radiation, and do they impact the system itself? Or if you put it on an oil and gas platform and someone says, yeah, this one's only 30 feet above the water and it's in the North Sea, someone who's an expert in the area immediately knows like whether they're worried about salt or they're worried about heat. So there's that aspect of it is going to happen. So a good way to think about robotics is the same way I think we're currently comfortable thinking about computers and cloud and infrastructure. Like, I think that we globally have a perspective of how complex that ecosphere is that supports computation for us. And robotics is the combination of that ecosphere that exists for computers and that ecosphere that keeps our cars running at the same time. And I think that's a lot for someone to absorb, but it's also something that most roboticists at least need to be exposed to all the different elements that are in it.
Fascinating. When we get the fusion reactors going, we get more energy out than we put in. Mm-hmm. And what will happen in the regards to robotics with this invention?
So, I mean, that already exists. I've had some great opportunities to work with a group called RACE. It's part of the Cullen Science Center where the fission.
We were talking about fusion or fission. I don't know.
Yeah.
Fission exists, yes, but
this is why we have students who take these classes, and I become too broad. But the robots already in that system are absolutely critical to its long-term success. They already use robots. In fact, they're teleoperated and everything is designed because when the plasma is moving around in a circle, it's contained, but the materials have to be replaced quite frequently to make sure that that's safe, because they just wear out, they become pitted and that kind of thing. And no human is going into that space. So it's already done with robots. The robots that they are designing to swap out the components in the tokamak and the larger systems that they're building in either South Korea or France, I believe, are huge. The robot elements sometimes are as big as trucks. And so it is that huge element of the mechanical design, the huge element of how do you make it easy to teleoperate? Should you even try to fully automate it? How do you design the system itself that they're going to have to fix so that robots can work with it? Because there are things that robots can work with better than other things. And then finally, how do you do the full FMEA, which is the acronym for Failure Modes and Effects Analysis. Like, what if this part breaks? What if that part breaks? How do we fix this? How do we fix that? And so it's a hugely complicated problem, particularly when you think about how positive the world wants us to be before the thing lights up, that we can address any issue that may, no matter how improbable, possibly come up. So it's a big robotics problem.
Super technical, but now for the marketing messages. We would briefly discuss the collaboration between the IMS laboratory and the Texas Austin Robotics Laboratory. So how are you guys doing with the interdisciplinary and intercontinental collaboration?
My immediate answer is, I mean, he's here. So that's a marker by itself. But yeah, I mean, there are active projects. So let me think back. I was in the States in 2017 to 18, I think. So it's been already like 5 years at least. And it's been constant collaboration in sense of, okay, we're in 2 different continents. But it's exactly what I'm introduced with my PhD topic is the software part of it. They have the different tasks, problems, robots, and we have like they're like on the software level, the collaboration is happening day in, day out. Like recently, the most fun project for me was like in autumn, I guess ChatGPT really picked up the pace. And initially I kind of ignored this, and then I was like, okay, let me see how well I write C++ if I just describe a problem, and it just delivered. So naturally I was like, okay, there are multiple things in my PhD work that what if I let ChatGPT create a sequence of actions or a task? Like I give the robot, like, go over there and check the battery status. And then if the battery is low, return to the charging dock, something like this, just a natural language sentence. And I gave a few examples of how I expect the results, but I never gave an example of this particular task. And of course, it created this technical description of a task that I could immediately shove it on the robot and execute it. And then we collaboratively worked on that. Like, what if we now take this and put it one of the cool dual arm mobile manipulators or in Austin, and that's exactly what we did. So me sitting here figuring out the GPT part, the engineering part of it, and over NRG, Fabian working on the robot, Selma working on the large language model aspect of it, like how reliable it is, how robust it is for different prompts, and it's still an ongoing project. So, and that's just one example of such collaboration.
He mentioned Fabian. Fabian got his master's here, and then went back to Columbia after the COVID timeout we all had to unfortunately take. And then he applied for a job in my lab. And when I saw he had experience with Tomoto, like I was like, oh, I'm going to hire him. Tomoto is the software that is
what has a code name for it
developed. And so that worked out. Selma is working on the large language models back at our place. She will be graduating soon, fingers crossed, which means who's going to pick up that element of it when it's not where I'm an expert. And it could turn out that the person that I try to work with on continuing the efforts with our large language models is a student, Agnes, here. I would love to maintain that relationship because that's a nice natural step. So one of the nice things about having 2 universities, 3 universities, 4 universities, but let's start out with 2 that are just this as collaborate as often as we do. The pool of people who can pick up the different threads that need to be picked up when you do applied robotics is obviously doubled. And there's a lot of skill here. There's a lot of skill there. There's a lot of tools there, tools here, and it's been a really good fit so far. Everything both of the universities does is based in ROS. ROS is the robot operating system that is the open source foundational software used by almost every university working in robotics today. And that's not any different for...
And companies are picking it up. It's not just in university toy anymore.
There's whole industry affiliate programs. Ross Industrial run out of the universities, and then here in Europe out of Fraunhofer in Germany. And so learning Ross, you're right, absolutely gives you a step up into industry as well. So, but Robert and I have both seen too many open source packages associated with Ross die because only one university kind of ran with it, and then that person graduated. And now, even yesterday when the students were doing the presentations in my class, oh my gosh, this hadn't been updated. So I'm trying to use this version of Ubuntu with that version of Python with this version of Ross, and spending so much time on this integration problem. All of our students are prepared to go out and contribute and use the open source software. But when you have more than one university actively engaged in keeping packages alive and developing and improving and adding features, things like that, then we are actually doing a collective better job of keeping those new capabilities developed at the University of Tartu and the University of Texas alive and improving throughout their life cycle.
I'd add to this, I completely agree with that. More people involved with something, a project, whether it results a software package or an actual robot or both. It is also that you guys have your domain of application, and we have our application domains, and this diversity gives us many opportunities. Okay, maybe you're in a usually you're not in a dry season in terms of projects, but if we are, there's a potential to apply the same system now at Austin. So if it was just us, say we have created this cool software, but without any motivation of where to apply it, you can have many people maintaining it, but if it's not being used, this motivation kind of goes away. But having more universities, having this collaboration gives the diversity of different application spaces, and that's definitely what I really, really appreciate.
Yeah, to add to that, also the University of Tartu's robotics is definitely matured in the ability to do things since probably Carl first came in the last 4 or 5 years. And then there's this building Delta that we're sitting in right now, which includes computer science, multiple lab groups, the robotics, the technology institute, things like that. One of the opportunities I had while I was here was to go out to the forestry and life sciences school that is east of here. Stefan, I wish I could remember his last name, but he's a professor in the forestry group, and just brainstormed up ideas on how they could automate the science, automate the procedures behind the science where they're collecting data on the health of the Estonian forests. And there are true opportunities there to use either big data, such as some of the other groups in computer science, or robotics. So to Robert's point, I think that there's also a real opportunity now with the capabilities here stepping
within
up
the groups
for applications of the robotic capabilities at Tartu to directly impact needs here as well.
Sounds like a call for collaboration.
Yes, I would definitely hope that I can help foster that here, because there's a lot of opportunities right here.
So as you all can hear, we have different possibilities for endless cooperation at the University of Tartu Institute of Technology. So what else to say? Join us and see you next time. Thank you guys for joining us.
Thank you.
Thanks for having us.